everyone, and welcome to e-sipnayan, your math guide through senior high school. So for today's video, we're going to discuss Lesson 7 of General Mathematics, and that is on exponential functions. Do not forget to like and subscribe to our channel, e-sipnayan. We have two objectives for today's video. The first objective is to be able to determine the asymptote, intercepts, and domain and range of an exponential function using its graph. Second objective is to be able to construct a mathematical model of a real-life situation that involves an exponential function. Let's first define what is an exponential function. So an exponential function is a function in the form f of x is equal to b raised to x with the following characteristics. First, the base or b is a real number greater than 0. So an exponential function cannot have a base that is negative. Second, the base cannot be equal to 1 because when the base is equal to 1 raised to any number is 1, therefore the function will just become a constant function. Third, the value of x can be any real number. Okay? So when you try to graph an exponential function, you'll notice that it only has one asymptote. It only has a horizontal asymptote. So say for example, you have the function f of x is equal to 2 raised to x. So if you graph this function, this green line right here shows the graph of the function f of x is equal to 2 raised to x, while this broken line here represents the asymptote. Okay, so this particular graph is asymptotic to the line y equals 0, and the asymptote y equals 0 is true to all functions, exponential function in its basic form. By definition, the domain of any exponential function is the set of real numbers because x can assume any real number. So we can write the domain in set builder notation like this. So this is read as x such that x is an element of real numbers, and this domain is true to any exponential function. Let us have an example. Say we have the function f of x is equal to 3 raised to x. So if we try to graph the function, the graph would look like this. Okay, so this green line right here is the graph of the function, and this red line here, broken line here, represents the asymptote. Okay, so since the red line here or the asymptote coincides with the x-axis, then we can say that the horizontal asymptote is the line y equals 0. Second is the domain of the function. So again, by definition, we know that domain of any exponential function is the set of real numbers. Thus, we write the domain as x such that x is an element of real numbers. Now for the range, we're going to take a look at the graph. So we can see that all the points in the graph are found above the x-axis. Therefore, we can write the range as y such that y is greater than 0. Let's move on to the x-intercept. So in the x-intercept, we determine the point where the graph meets the x-axis. So since the graph is asymptotic to the line y equals 0, therefore it would not meet the x-axis, or it cannot intersect the x-axis. Thus, the x-intercept does not exist. So the y-intercept is the intercept where the graph intersects the y-axis. So we see that at this point, the graph intersects the y-axis, therefore the y-intercept is the point 0, positive 1. Next, let's have the function f of x is equal to 3 raised to x plus 2. So notice that in this function, we added 2 to 3 raised to x, which is our example from earlier. So if we try to graph this function, the graph would look like this. Comparing the graph to the original function f of x is equal to 3 raised to x, you'll notice that the graph has the same curve Okay, it looks the same, but the graph and the asymptote moved 2 units upward. Okay, this particular scenario is called a translation. So when you add a value to the function or to the value of x, it translates the graph either upward, downward, left, or right. So in this case, since you're adding 2 to all the values of y, the graph translated 2 units upward. Okay? So let's try to determine the asymptote, domain, and range and intercepts of this function using its graph. So we see that the asymptote moved 2 units upward from y equals 0. Therefore, the horizontal asymptote of this function is the line y equals 2. Next, we know that the domain is your set of real numbers. So we have the domain as x such that x is an element of real numbers. The range, you can see that all the points in the graph are above the line y equals 2. Therefore, the range of the function is y such that y is greater than 2. Okay, now for the intercept, so we can clearly see that this particular graph cannot intersect with the x-axis. Therefore, again, the x-intercept does not exist. While the y-intercept moved from 0, 1, 2 units upward, therefore, the y-intercept now becomes 0, positive 3. Now let's try this function. So we have f of x is equal to 2 raised to x plus 2 minus 2. So if we're going to graph this function, the graph looks like this. Okay, so the horizontal asymptote is the red line here. Okay, so it is on negative 2. Therefore, the horizontal asymptote is the line y equals negative 2. Okay, now for the domain, again, the domain is the set of real numbers. And then for the range, you can see that the graph has its points above negative 2. Therefore, the domain is y such that y is greater than negative 2. So for the intercept, so the x-intercept, you see that the graph intersects the x-intercept at this point. Therefore, our x-intercept is the point negative 1, 0. Now, for the y-intercept, we'll take a look at the point where the graph meets the y-axis. Therefore, our y-intercept is at 0, positive 2. Okay? Now, let's try this example. So, we have f of x is equal to negative 2 raised to x plus 1. So, if we're going to graph this function, the function looks like this. Okay, so notice the red line still represents our asymptote. Therefore, our asymptote is the line y equals 1. Okay, and then the domain is your set of real numbers, x such that x is an element of real numbers. Now, notice that the points now are located below the intercept. Okay, therefore, the range of this function would now be y such that y is less than positive 1. Okay, now for the x-intercept, notice that it intersects the origin. Therefore, both its x and y-intercept is at 0, 0. So, let's try this example. See, we have the function f of x is equal to negative 2 raised to x plus 2 minus 2. So, if you're going to graph this function, the graph would look like this. Okay, so again, we take a look at the asymptote. So, the asymptote is the line y equals negative 2. So, it is this line right here. Next, the domain is your set of real numbers, and the range, notice that the points is below negative 2. Therefore, the range is y such that y is less than negative 2. For the intercepts, notice that this particular graph cannot cross the asymptote nor the x-axis. Therefore, the x-intercept does not exist. For the y-intercept, so the graph intersects the y-axis at this point. Therefore, the y-intercept is the point 0, -6. Now, let us try to use exponential functions in real-life situations. So, exponential functions may be used for situations that involves exponential growth or exponential decay. So what is exponential growth or decay? So it is a way that a quantity grows or decays over time at a certain rate. Okay, so if we're going to create a function that involves exponential growth or decay, we can follow the formula. So since it is a function, let us have the variables. So the first is the variable x, which represents the number of times the amount is increased or decreased, and y will be the amount after the elapsed time. So with this, to create the function, we use the formula y is equal to the initial value times 1 plus if it is in an exponential growth, or minus if it is an exponential decay, and then the rate of growth or decay, and raise that to the number of times the amount was increased or decreased. So that is x. So this particular formula will help you construct a function that involves an exponential growth or an exponential decay. Let's try this one. Bacteria are growing in a culture at a rate of 5% an hour. So initially, 400 bacteria are present. So let's write a function that gives the number of bacteria present given the number of hours elapsed. So before we write a function, of course, we have to represent the variables first. So since the number of bacteria is dependent on the number of hours, then we can say that the x is the number of hours elapsed, while y is the number of bacteria present. Okay, so according to our formula earlier, we know that y is equal to the initial value times 1. So we use plus since this is an exponential growth. So 1 plus the rate of growth raised to the number of times it will grow. So using this, we simply substitute I and R. So we know that the initial value is 400 and the rate is 5%. Therefore, our function would be f of x is equal to 400 times 1 plus 0.05 raised to x. So let's try to use this function to answer a problem that involves this situation. So given the same situation, how many bacteria are in the culture after 6 hours? Okay, so we use the function f of x is equal to 400 times 1 plus 0.05 raised to x. So we know here that the value of x is 6. Therefore, we simply substitute 6 to our function. So I have f of 6 is equal to 400 times 1 plus 0.05 raised to 6. So when you try to use your calculator to answer, you will see that f of 6 is approximately equal to 536. Therefore, there are approximately 536 bacteria in the culture after 6 hours. Let's have another example. So the value of a laptop depreciates by 7.5% every year. If its value this year is 35,000, construct a function that will show the value of the laptop after a certain number of years. So again, since we are constructing a function, the first thing that we need to do is to represent the variables. So it says here that the value of the laptop is dependent on the number of years elapsed. Therefore, x would now represent the number of years elapsed, while y represents the value of the laptop. So again, it says the value of the laptop depreciates. So it means it loses 7.5% of its value every year. Therefore, this is an exponential decay. Okay, so to create a function that represents an exponential decay, we use the formula y equals I times 1 minus, since this is an exponential decay, times minus the rate raised to x. Okay, substituting the value, so we know that the initial value is 35,000 and the rate of decrease is 7.5% every year. Therefore, we can write the function as f of x is equal to 35,000 times 1 minus 0.075 raised to x. So let's try to use the function to answer a problem that involves this situation. So we're using the same situation. The question is, how much will be the value of the laptop after 3 years? So using the function f of x is equal to 35,000 times 1 minus 0.075 raised to x. So we simply substitute 3 to x. Okay, so since our value of x is 3, we substitute that to our function. So f of 3 is equal to 35,000 times 1 minus 0.075 raised to 3. So using the calculator, we approximate f of 3 as 27,700.86. Therefore, the value of the laptop will be approximately 27,700 pesos and 86 centavos after 3 years. Now let us have this example. So the price of the fuel increases with inflation at 2.5% every 3 months. If it continues to grow at the same rate and the price of fuel this month is 41 pesos and 20 centavos, construct a function that will show the price of the fuel after a certain number of months. So we'll start first with the representation of the variables that we'll use in the function. Okay, so it says here that the price of the fuel is dependent on the number of months. Therefore, our x would be the number of months elapsed and y would be the price of the fuel. So since it is indicated that the price of the fuel increases with inflation, therefore we are going to use the formula for exponential growth. So we have y equals the initial amount times 1 plus, since this is exponential growth, times the rate of increase raised to the number of times it increases. Okay, so the initial amount is 41 pesos and 20 centavos and the rate is 2.5%. But it says here that it only increases every 3 months. Okay, so since our exponent should represent the number of times it increases in a year, we have to divide the number of months by 3. Okay, therefore our function would now be f of x is equal to 41 pesos and 20 centavos, that's our initial amount, times 1 plus 0.025 raised to x divided by 3. Now let's try to use this function to answer a problem that involves this situation. So, given the same situation, the question is what will be the price of the fuel after a year? Okay, so we have the function f of x is equal to 41.20 times 1 plus 0.025 raised to x over 3. So, when we say 1 year, it includes 12 months. So, we replace x with 12 since x represents the number of months elapsed. Okay, so substituting 12 to x, we have f of 12 is equal to 41.20 times 1 minus 0.025 raised to 12 over 3. So, using our calculator, we can see that f of 12 is approximately equal to 45.48. Therefore, the price of the fuel will be approximately 45 pesos and 48 centavos after 1 year. So, this is the end of our lesson. I'll see you all next video. Bye everyone!